Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And today we're going to be working on processing sound files. And we will do this both in MATLAB and then also in Python. And just as a quick note here, the most interesting sounds, at least in my mind, are those which have sinusoidal tones or sine tones. That's in terms of actually measuring the sound and then doing the post-processing, as we will see in some upcoming slides. So to start off with, nowadays there are so many different ways to record sound. Probably you already have a smartphone, maybe an Android or an iPhone or some other device, and it's very easy just to download an app and turn your smartphone into a sound recorder. So that's the image shown on the left. And then the image on the right, if you want to go out and spend a little extra money and get a dedicated recording device that has more bells and whistles, you can easily do that. And for a couple $100, you can get a device similar to the one shown on the right that you can go and do a high quality sound recording, and that might be particularly advantageous if you're going to record a fine arts performance of some sort. But mostly what we're talking about today is sort of field recordings where there's probably going to be some broadband random vibration, and if it's an outdoors recording, there's probably going to be some bird chirps and other miscellaneous sounds that are going to get into our recording. So for what we're doing today, just the smartphone is good enough. Now, for Android users like myself, there are different apps that can be downloaded, and the one that I like is called Sound and Voice Recorder ASR. It's simple. It works great, and what this app does is that it records the data and stores it in a format called .ogg. And we'll talk about this in an upcoming slide in regards to that format. But then once the recording is made, then that OGG file can be sent via email. So it's very simple and quick and easy to go out and make a field recording and then just email that sound file to yourself, and then you can do some post-processing on that signal in your desktop PC or your laptop PC. And I'm not an iPhone or iPod or iPad user, but I know there's similar apps available for Apple-type devices. Now, there's all sorts of different audio file formats, probably a dozen or two or 3 dozen maybe. But let's just go over some of the more typical ones, the more common ones. So at the top there, we have the MP3 file. That's a MPEG Layer 3 audio compressed format, and it's very popular for CDs, for example. Then the second one is the .ogg. This is OGG Vorbis. It's an open source format. It's also compressed. And devices like Arcos and Samsung Android type devices make extensive use of the .ogg format. Then there is the WAV format, and this format has very large file sizes, but it's a very convenient file format for converting that sound file into ASCII text data. And for our purposes, we do need to convert our sound file into ASCII text data so that we can do some post-processing in MATLAB or in Python. And if you'd like to know more about different types of audio formats, there's a Wikipedia site that you can go to. So what we need to do is we need to get our data into .wav format as an intermediate step. Now, let's assume that the data we've recorded, it's in MP3 format, or it's in OGG format, or maybe in some other format. So what we need to do is we need to go to a conversion utility. And there's a plethora of online tools for doing sound file conversion. And uh, most of these are free, or maybe they ask for a donation. And the one that I've used is the www.camcar.com. And I'm not here to be a salesman for any of these particular links or sites. The Zamzar is actually a free online resource, although you probably have to look at some advertising or something while your sound file is being converted. Or you can also download a freeware open source type audio editor, and it's called Audacity. And this will allow you to do some editing as well as convert from one type of sound file format to another. So again, with this PowerPoint slide here, we're assuming that we have our data in some format that needs to be converted into the WAV format as an intermediate step. Now, on the other hand, you may have a recorder that outputs the data in WAV format, so then you can just skip over the steps in this slide. So here's an example. Now, I've got this posted on my blog. I was a passenger in this CRJ 900 regional jet with turbofan engines. This is just a typical photo of the type of aircraft that I was in. It was a different airlines. And what I did is I made a recording inside the cabin as the aircraft was at its cruise altitude. And I did this just using my Android phone. And then I went through the processing steps and was able to do a spectral analysis. Of course, this was sound measured inside the cabin, so the fuselage walls were attenuating some of the sound. But of course, some of the sound also propagates through. And that sound, it's mainly generated airborne sound from these turbofan engines. There's also some direct structural borne sound from the turbofan engines. And of course, there's different aerodynamic type of effects going on as well. Plus, in the cabin of an aircraft, there's always just background noise from passengers and air conditioning equipment and so on. So let's go ahead, and we're going to go to MATLAB here shortly. And I've got a utility that will convert a WAV format file to ASCII text format. And we're going to use that sound file that I recorded inside that regional jet. So let's go to our MATLAB GUI, go to vibration data in the command window. And let's see what we're up to this week. Okay, we're up to version 5.5 this week. Let's go to Sound File Editor. We'll begin analysis. So at this point, we've taken our sound file and we've previously converted it to WAV format if it was not already in WAV format. So let's read in that WAV file. And it's going to be crj900.wave. And you can, if you like to work with this file yourself, you can download it from my blog, or you may have your own WAV file, your own recording. Which by the way, I highly encourage you to go out and make your own recording of something or other. Okay, now in this case here, we've got two channels, or you could say two tracks. So we have a green and a blue. And this MATLAB utility I've written does not do any type of mixing. Rather, what it's going to do is it's going to split this WAV file into two separate channels, one for each of the two tracks. And this utility will also work if it's just a mono signal. So let's see. Let me minimize that. Now we can play sound, and I could do this right now, but you would not be able to hear it. I don't have the right audio link set up as I'm doing this recording, but just know that you can actually play that sound from your WAV file. But what we want to do is, we can either save it now to ASCII text, or let's just save it for MATLAB Workspace. So I'm just going to be kind of lazy and call this CH1. That'll be channel 1. You might want to give yours a more descriptive name. I'm just going to have channel 1 and channel 2. So this is going to be the WAV file converted to text format and then exported to the MATLAB workspace. Okay, so I go ahead and save complete. Now, typically what we like to do once we get a sound file is do a spectral analysis to find out the frequencies of any sinusoids that might be superimposed in that sound data. So let's go to calculate FFT. So this actually the FFT script, we've run this before in previous units. So in this case we're going to have preloaded into MATLAB, and it's going to be CH1 and mean removal, yes. Let's leave window at rectangular. 500 hertz is going to be my maximum plot natural frequency. For our y-axis, so anytime we have a wave file, let's just call it unscaled sound pressure. The data we have is it's uncalibrated in terms of its amplitude. So we're not going to worry about how many dB it was. Let's go ahead and calculate our FFT. We get a magnitude and phase plot. We'll kind of ignore that one for now. And then here's just the straight magnitude. So we have Fourier transform magnitude. We've got unscaled sound pressure along the y-axis, frequency in hertz along the x-axis. And the software is already telling us that the maximum peak is at 104.2 hertz. Then the second highest peak here is at 252 hertz. So those are the two spectral sinusoidal type peaks there, 104 hertz and 252.5 hertz. So let's see if I've got a, okay, here's just showing you how we called up the WAV file into MATLAB as we prepared to convert it to ASCII text format. Then here shows the plot. Now I just demonstrated how to generate this plot, and here's the slide version of that same plot. And I've got a couple of additional notes here. Those two spectral peaks correspond to things going on inside each of the two turbofan engines. And it turns out that the turbofan engine has two shafts. They're not the same length, but they are concentric. And there's the N1, which is the fan shaft or rotor, and we measured it at 104 hertz. And then the second peak here is called the N2 core peak, and it's 252 hertz. And well, how did we know that this was N1 and N2? Well, what I did is I looked up some information on the model, that aircraft model, and what type of turbofan engine models it has. And I looked up some information on what the nominal or maximum, I should say, N1 and N2 rotor speeds were. And it turns out for those two numbers shown on the right-hand side of the slide, that would indicate that the engine was at 85% of its power. So it just makes sense, and it's just plausible and almost certainly true that the N1 fan frequency, which is listed just a little bit above 104 hertz, would appear at 104 hertz, assuming that 85% was the running power for those engines. And then similarly for this spectral peak at 252 hertz, the actual maximum frequency for that N2 core shaft is a little bit higher. Well, an important thing about turbofan engines is that the pilots do not run those at 100% power or maximum power, because if they did that, well, that would cause the engines to wear out prematurely. And then there's also another consideration, and I'm going to say fuel mileage. Now, in some of you might be pilots, and in the aviation industry, there is a more technical, more appropriate term used. But if I say fuel mileage, you get the idea. The plane can operate most efficiently if the engines are run at roughly 85% of their full power. and that's how the aircraft can achieve the most mileage for the least amount of fuel. Obviously, fuel cost is a huge cost in flying these aircraft. Okay, now everything we have just done in MATLAB, we can also do with Python. And again, as I get my Python ready for you here, go out and make a recording. It could be something as simple as an air conditioning compressor, or something with your automobile, or just something. Just find something to measure. I even had an instant where a while ago I had a plumbing problem in my house, and I had what's called singing plumbing pipes. Every time the water was run and then the valve was shut off, the faucet was shut off, there would be some residual humming that occurred. And I measured that and did an analysis. And later on we called a plumber to get that fixed. Okay, so let's go to our Python. And some of you like to use Python because Python is open source free. And I'm going to open up an interpreter here. And let's do run. So we're running our vibration data Python GUI package script here. And I'm doing it within the Spider environment. So let's go to sound file editor down here at the bottom. And this one looks a little bit different than MATLAB, but oh, by the way, this is up to version 4.7. Let's read in our WAV file. And it's just going to be the same one, crj900.wave. So there's our two channels again for this recording. Those are the time histories. We can also play that WAV file, and again, I'm not going to demonstrate that now because I don't have the right audio link hooked up so that you could hear that. But that's something we can do. And then we can export as a text file. So enter the output file name for channel 1, and I'm just going to call this ch1.txt. It already exists, okay. Overwrite. And then it's going to ask me what's the output file name for channel 2. Now this conversion utility will work if you just have a mono recording, or if you have a two-channel stereo type recording. And if you have more than that, then the software might have some problems. So please contact me if you have some multi-track recording that's greater than 2 channels. So after we've exported to text file, we can calculate FFT. So again, we're going to have unscaled sound pressure. And if you've been following the Python webinar units, you've already run this FFT function within Python. So let's read, and we're going to do channel 1. Now if you want to do channel 2, you can do that as well. In fact, maybe just for variety, let's do channel 2. Channel2.txt. Okay, mean removal, yes. Rectangular window, that's fine. Okay. Had to wait there, pause for a moment while Python completed the reading in of that file. Let's go from 0 to 500 hertz. Let's calculate the FFT. Okay. Now this channel looks a little bit different than the other one, but the spectral peaks should be at the same frequencies. So let's see what we can do for our, so there we have about 105 hertz. Now the cursor for the Python is not as smooth as the one for MATLAB. It just goes off the pixels here in Python, but it's good enough for what we want to do. So again, we have a peak at 105 hertz. I'm rounding off. And then we have the second peak at 252 hertz. So we can see the N1 and the N2 frequencies there. And, well, here's another one. Let's take a look at this peak down here. This is about 208 hertz. Well, it could be depending on how we look at some significant digits and round off, it almost seems that this intermediate peak here is potentially a 2 times harmonic of this N1 spectral peak there. So that's kind of interesting. Okay. I think that's going to about do it for our slides here. Let's see if I had any other slides here. Then the remaining slides here just showing that, well, here we are in MATLAB, back at MATLAB. Then we went to Python, and we got our Python FFT. This is the channel 1, so it looks a little bit different than channel 2, but the spectral peaks have the same frequencies from channel to channel. And the reason they're different, it could just be the way I had the smartphone oriented, or who knows, some other reason. I just want to go quickly to the blog. So let's see, got some other stuff up there that should not be of any concern to you, but let's go to vibration data. This is the classic web page for vibration data. Then I go to blog, and here's the blog entry for special topics sound file processing. So if you're interested in learning more about that CRJ-900 aircraft, you can click on this link, and I've got a blog entry that shows the aircraft, and then that's what the engine is. It's a GF CF34-8C5 turbofan. And then I've got the Fourier transform there. Some other additional information there. And then if you want to download that sound file in WAV format, there's a link to download that. And if you're interested in my singing plumbing pipes, I've got a blog entry for that as well. And it looks like I've got an MP3 file there. So if you want to download that, you could download it via MP3 file. Then you could do the conversion to WAV format and do an FFT. And if you do that, you'll find that the frequencies of my pipes in my home were 400 hertz prior to the plumber coming and doing the repair job. So I hope you've enjoyed this webinar unit, and by all means, go out and have some fun. Do your own recordings, and we'll see you next time. So thank you, and goodbye.